Good afternoon, everyone, and welcome to Western Sydney University's National Science Week event from the International Centre for Neuromorphic Systems. Come, let me show you inside. Our talk today is titled Tracking Space Junk, Building Brain-like Computers, and Self-Playing Pinball Machines. And today we're going to talk about all that and more. And what else we do here at the International Centre for Neuromorphic Systems. We'll give you a tour of our facilities, introduce you to our researchers, and at any time, please feel free to ask us questions on the online chat, and we'll answer them during a series of question-answer series over the next 1.5 hours. Right now, however, let's go across to the director of the International Centre for Neuromorphic Systems here at the Marx Institute at Western Sydney University, Professor Andre van Schaik.
Hello, and welcome to our open day at the International Centre for Neuromorphic Systems. My name is Andre van Schaik, and I'm its director. We would love to take you on a virtual tour of our lab today. First up, you're probably wondering what neuromorphic systems are. Well, neuromorphic means we're learning from neural systems in biology, such as eyes, ears, and brains, and applying what we learn to electronics to build smarter devices. Why would we do this? Well, take for example a mosquito. It only has a tiny brain. But if you've ever tried to catch a mozzie that's keeping you awake at night, you know how good it is at flying and avoiding getting caught. In fact, it's much better than any flying system we have ever built. On top of that, the energy it consumes is about the energy contained in a single grain of sugar. So they are very efficient. By taking inspiration from biology, we aim to build highly capable and efficient electronic devices. So we develop a host of sensors inspired by biology and algorithms that process the data we get from them. Today, we will show you some of these sensors and how we use them. Because we want to show how good our neuromorphic systems are, we are always looking to apply them to real-world tasks and problems. Because of that, we do a significant amount of our research in partnership with industry and government. You might not realize this, but the group we have here at Western Sydney is one of the leading groups in the world. On top of that, we have partnered with the other leading universities in the fields to have access to the best minds in the world. I hope today we can convince you of the interesting research we do and that it is worth looking to understand neural systems in biology to build better electronic devices. Once again, welcome to the International Centre for Neuromorphic Systems and enjoy your visit.
Well, thank you, Andre. All right, so let me tell you a little bit about the technologies that we're going to show you today. And the most important one perhaps is the neuromorphic vision sensors we work with. Now what these are, they're like cameras, except they work more like a human eye than a normal camera. It doesn't take photos. It produces information only when things change in the field of view. Now that's pretty convenient because we have one right here. And I can show you how it works. So the difference with these cameras is because they only detect changes, and they only send you information when something is moving or changing the scene. When nothing is happening, you get no data out of them. So the amount of data and power they use is much lower when nothing is happening. Compare that to a normal camera, which is pulling pictures out continuously no matter what's happening in the scene. So when I stand still, I disappear. But when I move, only the pixels that generate information, only the pixels that see changes generate information. And we're going to show you how we're using that to do some really, really exciting things. We can use it on telescopes to track satellites in space, for example. We're going to talk about how we're trying these underwater to see what happens when you look through the marine environment. We're going to show you how we're putting these on robotic foosball tables and pinball machines to see if we can figure out how to play them better to sort of the way a human being plays them. And we're going to show you some other sensing modalities too. For example, how we're using similar ideas to build biological ears or cochlears that can listen to the world in a more biologically inspired way. So, with that, let's take a trip to my office where I'll tell you a little bit more about our astrocyte containers and how we're using these cameras to track space junk. This is our lounge area, our kitchen, and of course, our ensuite mini golf course. No lab's complete without a mini golf course. Welcome to my office. Alright, so let's talk a little bit about the astrocytes, which are our mobile neuromorphic containerized observatories. So these are telescopes and shipping containers that we can put anywhere in Australia and use them to do things like track space junk. And I'm going to tell you why that's important.
So why solve this problem? Well, We've been launching objects into space for 60 years now, and space is getting pretty cluttered up there. And this is a growing problem because we're reliant on space for almost every aspect of modern life, from communication satellites to GPS to critical defense and weather systems, for example. The problem is, of course, that every time we put a satellite up, the risk of collisions increase, and collisions in space can be catastrophic. These objects are moving really fast around the Earth. And if we don't do something soon to look after our infrastructure, we could have disastrous consequences. Of course, to the extreme of something called the Kessler effect, where one satellite collides into another, sends high-speed debris in all directions that hits other satellites and destroys them, creating this debris field that locks us into Earth. Now, of course, that's the worst-case scenario, but these are things that we have to start thinking about as we put more and more satellites into space. Just think of these mega constellations that SpaceX, for example, are thinking of putting up. So the trick, of course, is that in order to start cleaning up space, which is something we don't really do, or even just policing and regulating it, we have to know where everything is and how bad the problem is. And that's when neuromorphic cameras can help. By putting these on telescopes, we can absolutely detect and track satellites in a completely different way and unlock new ways to do what we call space traffic management, space situational awareness, or space domain awareness is the new term for it. So let me start by talking to you about our team. So these are the people who really made it all happen. And the team since then has grown. We have a whole bunch of new people working on algorithms and ideas and applications and refining the technology. But it's this core group of people over here and our funders, the Air Force and Plan Jericho and DST, who really took the idea from literally a sketch on my boarding pass like this. This is the real thing, actually. This is how I pitched it. All the way to this, a fully functional containerized observatory at the Avalon Air Show last year. We did this in a couple of months, which was fantastically incredible. And it was just a testament to the fantastic people I work with that we managed to do this. And it wasn't easy. We had to fabricate a specialized shipping container with a sliding roof. We did it literally first time we'd ever figured out how to do this. We had to figure out if everything fit. Telescopes are actually quite complicated. They move in strange ways. And for people who work in space, we haven't got the best spatial awareness. So we had to actually make little 3D models and move them around to make sure everything fitted. And after a few months of really hard work, we landed up with this. This is the AstroSite. It's a mobile telescope observatory built into a shipping container. The roof slides. Right? It's a mechanical sliding roof, and a scissor lift lifts the telescope up. And essentially, you can put this shipping container down, plug it in, slide the roof off, raise up the telescope, and do space imaging straight away. And the great thing about building into a shipping container is that there's an entire industry built around moving these things around. There are ships, there are trains, there are boats. This is a standard shipping container that can be moved relatively easily, which means we can pick up our observatory, move it easily, and put it down somewhere else. I'll show you how neuromorphic technology lets us do that, how it makes us less sensitive to the motion. I should say there's also a little office in there, so we can actually conduct experiments from in there, and I'll show you what it looks like inside. But the question really is, well, what does neuromorphic cameras do to help us with space imaging? Well, it turns out that space imaging is actually a really good application for neuromorphic cameras because it's all about contrast. Space is dark, and we're looking for bright things on a dark background. We're also looking for things that are very fast, they're moving quickly. And that's where integrating cameras become a bit of a problem. So what we found is that we're really good at capturing things like satellites with these cameras. Not so great at taking pictures, but then again, if you want to do tasks in space, you don't really want photos. And what we found is that we can also use these cameras. So we're leveraging the high temporal range to move the cameras. We can move the telescope and image whilst we move. And that opens up a whole range of really interesting possibilities, such as being able to track objects and follow them. We can also use the high dynamic range of the sensor to do a lot of this during the day. Now, if you think about a telescope observatory, if you can only operate at night, you're only working half the time. If you can operate during the day as well, you've doubled your efficiency, which isn't bad for a day's work. On top of this, we can also use the fact that there's actually less data. We don't need all that black sky. If it's dark sky and nothing's happening, we don't care about it. If something shoots through the field of view like a satellite, not only can we detect it quickly, but we can start tracking it straight away. So what I'm going to show you now is some telescopes. This is the first set of telescopes we ever used for these experiments. This was done in Adelaide with DST, and I really like these because this is where it all began. And if you look at the left-hand side there, you'll see two telescopes. They're actually on a mount that can pivot much like the one on the right-hand panel there. So we can point accurately at the sky. And the two telescopes are both-sided, so they're looking at roughly the same thing. What you might notice on the top telescope is that big camera at the back. Now that's a finger length instrument astronomy camera. It's a beautiful camera, but especially built for space imaging. It's actively cooled. It's a real it's a real high performance, well built camera. If you look at the bottom telescope, you'll see, in fact, one of the old ATIS prototype cameras hanging off the back there. That's a shoddy event-based camera that I put together myself. I say shoddy because you can actually see the screws hanging out of it. But essentially, I like the contrast here, which is to say, this performance we're seeing is with a camera, an event-based camera that wasn't built for this task, compared to an astronomy camera that's specifically for that task. If you look at the middle panel, you'll see that the top telescope with the astronomy camera has this aperture, which is just a cardboard box with a hole in it. Now, we needed to use that aperture in order to look at bright objects like Jupiter, which I'll show you in a second. Whereas with the event-based camera, we never have to touch the objects. We use the high dynamic range of the camera, and we can see not only just at night with this, but during the day as well. So sort of focus and forget. And that's really important if you want to put these cameras in remote places and not have to worry about changing lenses or having mechanical systems to do that. We then moved on to this 3 telescope setup that you see to your right-hand side. And that one has actually both a ATIS and a Davis, so we're comparing cameras and how they work. I'm going to show you the first results we ever got with an event-based camera on a telescope. And this is Mars. With an event-based camera, this was a really big deal because we had no idea what we were looking for, what it would look like. And in fact, you might notice it bumps up and down a bit. That's because we were excited and jumping up and down next to the telescope. But you also might notice there's this oscillation, a sort of circular pattern to it. And that turns out to be atmospheric scintillation. And that's a really interesting phenomenon in itself. And in fact, we have a project to explore the applications of these cameras in adaptive optics, because we're capturing this really fast. And we actually use that to compensate for the motion of the atmosphere and do better astronomy. So from this, roughly around the same time that night, we're looking at a different part of the sky completely randomly, just staring. But all of a sudden we saw this come through the field of view. And we looked at this and we thought, what is that? Started a whole bunch of lively debates. And after a while, we realized it's a low Earth orbit satellite. And that was kind of the aha moment for this work. We're like, oh, this is interesting. This is something you can't do with a normal imager. So this really led to the whole project and ultimately to the astrocycle containers I'm going to show you in a second. So what we did next was then point the telescope specifically at these objects. So this is what it looks like. If you look on the left, you'll see a frame-based representation of the data. And you can see why it really doesn't do it justice. You can see it's just a dot on the frames or on the frame-based rendering. But if you look at the spatial temporal data with time as the vertical axis, you can see it's actually a real rich stream of events as we move the telescope to keep this satellite in the field of view. What you'll see flying through the field of view are stars. And there's actually a lot of information in that stream of events. Sometimes we can tell things like if the satellite's tumbling. And as we explore more and more, I'm sure we'll find out other things we can characterize and determine from that event stream. Now I'm going to show you something slightly different now. I'm going to point the camera at the Jewel Box cluster, which is a beautiful collection of stars. If we look at them through a telescope, you'll see that they're actually quite colorful. And what you'll see here on the far left-hand panel is a frame-based output from a camera looking at the Jewel Box cluster. In the middle, you'll see the event-based output. And what you'll notice with the frame-based output, as you move the camera back and forth, the stars disappear because you can't see them when you're moving, you get motion blur. But on the event-based camera, it's exactly the other way around. It's actually hard to see the stars when they're stationary, but when the moment you move the telescope to back and forth, the stars jump out. And this is really where I see event-based vision and conventional cameras for astronomy working together. They're complementary, not a replacement for each other. And this is really where we see all the applications for event-based cameras and being able to image whilst you move, use that to your advantage. So let me show you what it looks like inside the astrocyte. Here's me actually grabbing that data the other day. You can see it's quite a little bit of a command center. This is inside the astrocyte where the telescope's just off to my right. It's actually quite a nice, comfortable place, both for the desert with an air conditioner. But of course, there's no reason why I have to operate it from inside there. This is built to be remote after all. So sometimes, on a nice day, I might choose to sit outside and operate it from here. And of course, there's no reason why I have to do it on campus. I could do it from home. Or, for the same token, I have someone in Europe do it during office hours for them in the middle of the night for me. So this is the whole idea. Eventually, and this is where we hope to be soon, is to have these completely autonomous, where they collect data and just send us the results. We tell them what to look for, and they come back with information that we send to a central point. And if we only capture what we need, the amount of data we have to send is far lower. So now I'm going to show you Jupiter. Here's the telescope going up, and you can actually see Jupiter just to the top right of that image. So that's a really bright dot in the sky over there. Now, when you point an event-based camera at that, here's the frame-based output of Jupiter and the event-based output. And you can see it's quite beautiful. You can actually see 3 of its moons. And what you'll notice is that as we move the telescope on the event-based camera, it's really nice and smooth. You can see the stars moving, but you can see on the frame-based camera that it blurs. This is the problem with stability. When you move conventional cameras around, you get this blurring effect, and that makes it really hard. In fact, most satellites and conventional images look like streaks. Now, I'm going to do something that's going to upset any astronomers in the room. So please, if you are an astronomer, I would suggest looking away now.
So this is what you absolutely shouldn't do around a telescope, just for the record.
So this is the idea of using near cameras to get motion insensitivity. Essentially, not only does the motion not really bother us, in fact, we can actually use it to our advantage. It helps us see things. So now you can understand why when we put these telescopes somewhere where the ground isn't necessarily stable, or we're near to a road on top of a building that vibrates, it doesn't really harm us. In fact, if we know something about that motion, if we can measure it, for example, we can use it to extract even more information from the scene. So it's a whole different way of doing imaging. And that's something that's really exciting. Now, I haven't talked so much about the algorithms that we're using it, but I'll give you a little taste of that. So what I'm going to show you next is probably the pinnacle when a whole bunch of different technologies come together with these. And what we're doing here is we're tracking a satellite like before, and that's in that red circle over there. It's a bit hard to see, but it's there. And we're moving the telescope to keep that in the field of view. And what you're seeing in that top left panel is all the stars moving through the background. Now what we can do is take those stars and build this beautiful star map they see in the background of that image. That star map we can then use to figure out exactly where in the sky we're looking. You can use it to do the place solving, the astrometry, and figure out exactly where the telescope is pointing without having to use expensive software or very calibrated mounts. This means in the future we're going to use really low power, low complexity hardware rather than using these expensive telescope mounts to move the telescopes around, and yet still figure out just from the information that we're seeing exactly where we are whilst we're moving. We can then use that information to infer how the telescope is moving, and what we do is compare that to the actual known motion of the telescopes we have to figure out how well we're doing, and it's actually extremely good. And we can also do other things, for example, like take two cameras on two different telescopes at different fields of view and have sort of foveated vision. We can go off and follow objects of interest in the sky. There's a whole range of possibilities of what you can do with these event-based cameras on telescopes that you cannot even comprehend or do with a conventional camera. And that's the really exciting application for this technology. So what I'm going to show you now is just a little sneak preview of what we've just built, which is our second astrosite. This is astrosite 2. You might notice the colors are inverted. What we've also changed here is changed the mount around. If you look on the right-hand side there, you'll see that as opposed to the previous mount, this is what we call an azimuth elevation mount. And that'll give us some really interesting abilities. For example, it can move a whole lot faster than the previous one. It's also good for tracking other objects in the sky, like planes. And what we plan to do with this is we plan to put these two astrosites in different parts of the country and start synchronizing them to do ranging. So not just figure out where the satellite is, but how high above the ground it is. And that's something that's extremely hard to do optically. And this is essentially where we're going to put one in Adelaide, one in Sydney, for example, and use them together to operate a network. Our goal, of course, is to expand this network across Australia and build a really interesting and fantastic space situational awareness or space domain awareness system across the country.
Let's look now at how we can use the astrosite in these telescopes remotely. And to do that, I'm going to go to my PhD student who can show you how he can operate this from the comfort of his own bedroom.
My name is Nicholas Ralph. I'm a PhD student at Western Sydney University in the International Centre for Neuromorphic Systems with the Marx Institute. My thesis is in exploring space domain awareness using neuromorphic event-based cameras. Space domain awareness is about understanding the complex environment of space and what's up above us, natural and artificial man-made. So there's usually satellites, and as a society that relies heavily on space infrastructure, this is really important to understand exactly what's happening up there to mitigate collisions and issues with this infrastructure. And so we use biologically inspired neuromorphic cameras, which have unique capabilities that we don't have with conventional cameras, namely their speed, their efficiency, and a much wider range of observing times. So I'm working from home during the COVID crisis, and from here I'm able to access the astrosite, which is our remote observing platform, which features high-powered telescopes with conventional, typical cameras you'd see, as well as neuromorphic cameras, and connect to that completely remotely from here, my house, and perform all my experiments, collect all my data. Okay, so I'm going to start our startup procedure. So the sky is clear, wind's not too bad, there's no rain, and it's dark. And I can see on our all-sky camera as well that we've got just a tiny bit of cloud or a smudge on our lens, one of those. Okay, so I'm going to open our roof. We have a weather event that we need to reset. That's fine. Okay, so roof open. Okay, and our scope camera will update now to show us what's happening in the observing side of the astrocyte. Okay, so we are open. I can now connect to our telescope mount, provide power to all of our cameras and cooling. We don't need dew heating right now. Okay. All right, and now I will raise our lift. So Greg, are we right to do that?
Good to go.
Okay. All right, raising the lift. Here we are. So we can see our telescope coming up now. Okay, so we look raised. All right, the first thing I'm going to do is just see what we have up at the moment. Okay, all right, so we have slewed the telescope to a nice bright star. You can see here, this is the feed from the event-based camera. On the left-hand side, we have the APS pixels. So these aren't your normal event-based pixels. They actually collect information about the intensity of the objects you're looking at. And then here we can see on the right two images, the event-based pixels. All right, so here in the middle figure, you can see the raw events that we get from the event-based camera, from the neuromorphic camera. And here we have the white dots are spikes, positive polarity spikes, and they're returned when there is a positive change in contrast, but we get the black dots when there's a negative change in contrast. So in other words, you get a white dot when something goes from dark to light, and a black dot when it goes from light to dark. Now here we can see our star in the middle, and we have, it sort of almost looks like it's swirling, and that's the effect of turbulence. This is in the atmosphere. So light, as it passes through the medium of our atmosphere, which has different thermal properties, will deflect, and we sort of get this swirling pattern. And on the right hand side, we have what's called a linear, an exponentially decaying time surface. And a time surface sort of decays slowly. It's almost like it shows longer term effects, because the event-based camera moves very, very fast, and the pixels on this figure here will move a little bit slower. It will sort of decay away. Almost looks like a heat map.
Oh, well, thank you so much, Nick. That was fantastic. All right, so let's take a look at our second astrocyte, astrocyte 2. So let's head downstairs to the loading dock outside this building, where we're building the second astrocyte.
Well, I'm Darren Mabel. I'm a technical officer here at the ICNS group. I work mainly on the astrocyte project, which is where we are now. This is specifically astrocyte 2. My background is from physics and embedded systems and astronomy, and I came to this project through working on the Western Sydney University Observatory. We're basically making an observatory in a portable facility that we can take anywhere, dump it down, leave it and operate it anywhere from anywhere. Mobility and telescopes generally don't go hand in hand, especially high-performing telescopes like this one is. So it's a challenge to make something like this perform and be mobile. Well, the telescopes that we're using here are fairly standard astronomical telescopes. Any person could go and buy something very similar from the store. The mount is a standard astronomical mount, except it's a very high-end one.
And it's completely automatic, right?
That's right. Yeah, that's the goal, to have to be able to operate it manually, remotely, and to have it be able to operate autonomously as well.
So this is building on what we learned building Ashes Like One.
That's right. We've made improvements, and when we started this project, we didn't know how to do it. Nobody knew how to do it because no one had done it before. So we've learned along the way. We're now working on Astro Site 2, and we're very happy with the results so far.
And waiting for Ashes Like 3, 4, 5, 6, and 7.
Hopefully, yeah. Hopefully I'm around when we get up to about 14.
All right. So end of the year. All right. So we're back in the lab. This is the space bar over here. And now we're going to have a quick question and answer session. So if you have any questions, now's a really good time to type them into the chat.